In the previous video, we started our discussion of grid-connected PV system design. We will now continue by further configuring the PV module's topology. Dividing the nominal DC voltage of the inverter by the averaged maximum power point voltage of the PV modules, we find the number of modules that should be series connected in a string. Next, we determine the number of parallel connected strings. This is achieved by dividing the total number of required modules by the number of series connected modules. Just as with the total number of modules, the number of parallel connected strings should be rounded up to the nearest integer. Having picked an inverter, determined the number of series connected modules in a string and the number of strings connected in parallel, we now want to know the efficiency of the inverter. We start by finding the instantaneous efficiency of the inverter. To that end, we will use an inverter model such as the Sendia National Laboratory inverter model. According to that, the inverter efficiency is a function of the PV array's DC power and its corresponding DC voltage. The DC power is the product of total number of modules and the power generated by one PV module. The DC voltage is the product of maximum power point voltage of a PV module and the number of series connected PV modules. Through the SNL model, we obtain the instantaneous efficiency of the inverter. This model is explained in detail in section 20.4.1 of the Solar Energy book. We can now determine the overall performance of the PV system. We start with the instantaneous AC power, PAC, generated by the PV system. It is a product of the total module area, instantaneous incidence irradiance, and all the individual efficiencies associated with the PV system. Those are the PV module efficiency, inverter efficiency, maximum power point trigger efficiency, and the other efficiencies. Generally, a fixed MPPT efficiency of around 98% is used. For a more advanced analysis, you can also calculate its instantaneous values by coding and simulating the MPPT algorithm separately. In the other efficiency parameter, soiling, cabling, and any other losses that could occur in a PV system are included. This efficiency parameter is usually set at 97%. Following the instantaneous AC power, the instantaneous system efficiency at a system can be calculated. The system efficiency is equal to the AC power output divided by the power incident on the modules, which is equal to the product of the total module area and incidence irradiance. Next, the instantaneous AC side yield, ACY, which is also known as the performance ratio, is calculated. It is obtained by dividing the instantaneous AC power by the nominal power of the PV modules. The next set of parameters considers the performance over a time period of a year. The annual AC energy yield, EACY, generated by the PV system, is obtained by integrating the instantaneous AC power. The yearly efficiency of the system, eta system Y, is calculated by considering the ratio between the AC yearly energy yield and the total irradiance reaching the module. Finally, the system performance can be expressed by an additional parameter that describes the yearly electricity yield, EY. The yearly yield is equal to the ratio of AC energy yield divided by the installed capacity of the PV system. It is denoted in watt-hour per year per kilowatt peak. The final step involves checking the design. We compare the annual energy generated by the PV system against the energy consumption of the loads. If the energy generation exceeds the load demand, the design of the grid-connected PV system is approved. If this condition is not met, the design process is reiterated with an increased sizing factor starting from the energy balance step. In summary, in this video you learned how to design a grid-connected PV system. We started by determining the total number of modules required to meet the load demand. Then we selected an inverter and correctly configured the PV module topology based on the inverter parameters. After completing the design, we calculated the performance of the PV system and performed a design check.